Hello, August the 1st. Alright, let's do this. Combinations. Old problem. Give integer k, return all possible combinations of k numbers from 1 to n. If I remember correctly, this is can use backtracking, right? Yeah, if I remember correctly, it's backtracking, which means you set the first one, you give me all the combination for the remaining, and then yeah, I think backtrack. No, not backtracking, just regular recursion. I think regular recursion shall be able to handle this. Oh, hold on. It's August. Wow. Time flies, man. Time always flies. Alright, let's see. If I remember correctly, n and then k combination is this, right? So we're given this depending on how many. So what we want to do is, given the current value, right? Given the current value, and then we take it, right? We take the current value and then do basically k minus 1, right? And maybe I can do this directly. I don't know. Let me say if k equals to 1, I will return n, right? If k is 1. Otherwise, we will take the current and then we'll do n plus 1. We'll say combine n plus 1, k minus 1. Right, starting from n plus 1. Actually, no. For I in range n plus 1 to what? It's a good question. Yeah, because def helper what? This is the current value. Current value, file, and how many remains. Okay. Now we say if remaining is equal to 1, we'll return the value. Otherwise, we'll take the value. So it can be value plus 1 all the way to n, right? And for each one, we need to get k. But it has to have enough, right? It has to have enough, which means from value plus 1, right? From values plus 1. So we shall check, right? We shall check. Impossible case is from value to n, we don't have enough. Oh, actually, we should do from value to n. We shall say if n minus val plus 1 is equal to k, it's smaller than k. No, it's, yeah, smaller than k. I won't have enough. Smaller than, I don't have enough, so we'll return empty. And if n minus val plus 1 is equal to remaining, right? Then we'll return list range val to n. If remaining is this, then we'll return this, right? Otherwise, then we go from this, then we do helper I remaining minus 1, right? So there's going to be combination will be this, right? I'm going to say if combination rest can be this. If combination rest.append val plus combination, and now we return rest. And we run helper. We start from 1 with k remaining. And we'll return this. Is this correct? 4, 2. Not sure, I was doing it pretty fast. NK. Combine. Let's sort them. Nope. Oh. I can say for com in one two one three 1 4. Oh yeah, sure. We have to go. We're starting from, yeah, this is starting from value giving anything. So we have to starting from 2, starting from 3. So on the outside, I have to do something similar. Rest equal to this. Right, I'm going to say for I in range 1 to n plus 1. Rest.extend helper ik, and now return rest. Yep, this seems to be right. We wanna, I guess, to get to 20. Usually 10 is the highest. So this is correct. So we're good to go. Ooh. I think we're time out. Can we value with remaining? Yeah, I can. And cache it. I think it makes sense, right? Given the value, how many can, yeah, it makes sense. But this one be faster if I cache it. Oh, it's still slow. Well, it's about twice as fast, so I guess it's fine. I was using Java last time. Does it count as DP? Yeah, I think it counts as DP. Helper val rem gives all the combinations starting from val with rem number of elements. We also use DP. We also cache the results. So what was the good solution? Yeah, it is backtracking. Okay, let's try the backtracking. Yeah, I thought it was backtracking. So the def helper. All right, and then we can say rest on the outside, and this is combination, can be a list of int. Okay. Then what? If len combination is equal to k, then rest.append combination, right? Else we can add the value, else what? We add the value and then we move on. So at the start we have nothing, right? And every time we shall go through everything, because the current we want to put it in could be any one of the value. So we can say for I in range from val from val, because I want to do from this. So we add value to the combination, right? We add value and then we try this, or we skip value, we do the next. So maybe we should val to n+1. Can say combination.append I, and then we call helper I+1 combination, and at the end pop. Now we don't return anything. And we simply call helper. We start from 1 with this, and then return rest. Yep, I think that's also correct. 1320 was this. Yeah, this is I think this is more official. Okay. This is the more conventional solution with backtracking. Basically, each we're starting from a certain value, right? And then with the current combination, so we add, right? At every position we can add all of them, and then once we add, we have to keep going on, right? Have to keep going on. At a certain point, and we can now going on, and that's the end. I don't know. I mean, the first idea is dp value with remaining. How many is this? Value with remaining. I'm gonna do all of them. I guess it works. This is actually very similar to mine. But I saved something here. Alright, it's okay. It's an old problem. Alright, let's give this a little bit of time. Just give one shot. If it fails, we'll do it tomorrow. You're given undirected, weighted, connected graph, n nodes and n-1. 0 to n-1, and interior edges, so we have edges. indicating there is an edge. Okay, some edges have the weight of -1, while others have positive weights. The task is to modify all edges with value -1 by assigning them positive integer values in the range so that the shortest distance between the node's source and destination becomes equal to an integer target. If there are multiple modifications, that make the shortest distance between equal to target, any of them will be considered correct. Turn the array containing all edges in any order if it is possible to make the shortest distance equal to this. So only -1 can be changed by assigning positive values. The shortest distance between the nodes and destination becomes equal to an integer target. The shortest distance between. So it's like Dijkstra, right? Dijkstra, what's that? 100, maybe. Maybe. Look at the number of hints. Did you see the number of hints? Jesus. What's this one originally? We have 0, 3, 4, 1, and 2. So 4 1s -1. 2 0s -1. 0 3 is -1. For everything is -1. Jesus. And we can modify, right? Is to modify all edges. All edges. So everyone has to be modified by assigning positive integer so that the shortest distance between the source. Source is 0. So this is source. And destination is 1. Well, the shortest distance between this equal to an integer target. Any of them will be considered correct. The graph above shows a possible modification to the edges, making a distance from 0. So on the 0 to 1, so this has to be 5, right? This has to be 5. And we have to make sure this is the shortest. Yeah, it doesn't really matter. In this case, you can change anything. Because there's only one path to 1. Right? Because there's only one path between them. There's only one path. And everything will be positive. This is already 5. This is -1. It is not possible to make the distance between 0 and 2 to 6 by modifying, because it doesn't go through this. This is interesting. So we have 1 2 3 4. Okay, 1 2 3 4. Oh no, 1 2 is 0. My bad. So this is 4. 1 and 2 is 3. 2 to 3 is 5. This is -1. So in this case, we want to change. So this is source, destination, target equal to 6. So here, from the source to the destination, we have 2 paths. One path is 7, the other path is 4. So this one has to be turned into 1. So what are we returning? Just return all the edges. So, I mean, no self loops or repeated edges, but there could be a loop overall. So you have a start, you have a destination, so we can find all the paths, right? We can find all the paths to it. Okay, so you find all the paths to it, and for each path, but the requirement is it has to be the minimum, right? So if you get all the paths, right, you can get all the edges, right? You get all the edges. That could be tuples, right? Something to something. So it will be no 1, no 0, no 1, some value, no 2, no 3, some value. So a path could be many of these edges. And they have different paths. And each path, if the path contains all, if the path contains all positive, right, and then the value is already smaller than the target, then that's impossible because we cannot change the positive. If the path contains positive and it's larger, then that can be ignored. If the path contains negative, then that one is something we can consider. So now we just have 1 path, 2 paths, 3 paths, doesn't matter, all the paths, and with all the edges, right? We have all the edges. Doesn't matter, we have all the edges. And what we want to know is the -1 in there, right? We have the -1 in there, so sum has -1. And what we can get is all the positive we can add together, so we can have a value plus some edge, some edge, some edge, and you have to make sure that one of the paths is negative, or yeah, the shortest path, right? The shortest path has to be of target, right? The shortest path has to be the target. So we can say, let's say, what if we say like the first path? What if this is target, and you have all these values, and you need to try. So you know the sum of these. You can get the sum of these, but if we have multiple edges, it can be, So basically, it's like it's a function, right? You have all the edges. So we have some edges. The sum has to equal to some value, and then some of the other edges plus some. This has to be larger than the target, right? Plus something. Basically, we have some edge equal to some stuff, and then some edge larger than some edge larger than some stuff. And we need to solve this equation to obtain one possibility. Now, how are we going to solve this? We can get all the edges, right? Get all the edges, then we try to add them together. And I mean, we can try, I guess. Like if well, if there's an edge that contains, if there's a path that contains edges that do not exist in the other paths, that will be the one, right? You can always make that the one, and all the others can do whatever you want. It doesn't really matter. Okay, that's the easy case, right? That's the easy case. That's the trivial case. So what if the edge exists in many different paths? Yeah. What if the edges exist in many different paths? You have some edge in this path, and that edge exists in the other path, right? So if you change it, you're affecting the other one as well. Ooh. I don't know. I mean, if I want to analyze, I might say I want a path that contains edges as least shared as possible. So maybe for each edge that's in, right, that's in a path, I can know how many paths this edge is part of. Okay? That I can do. I can do how many paths each edge is involved going from source to destination. But hold on. What if there's a loop? We don't have to consider loop. I think I can just BFS this to make sure there's no loop. We'll BFS from source, right, to destination, and then we can get, all the paths. But I don't know about that. BFS. And DFS shall work as well. We just don't visit the things we have visited before. Yeah, I think DFS shall work as well. It would be easier, right? So DFS will get all the edges, all the paths, and then for each edge in the path, we find out how many paths each edge belongs to, right? So some edge will belong to one path, some edge will belong to multiple paths, and of course we'll prune or trim, like all the edges with positive, we can just get rid of them. We'll only have the paths with at least one negative, right? And then when we compute this, how many paths are an edge is a part of, we only consider the edges with the negative values, right? Okay, so we have negative value, have negative edges, and each one has a bunch of paths attached to it. Then we can say the one that's associated with the least amount of edges. So they're like unique. So we can consider that. But again, it's not like systematic, right? It's not systematic. It's not systematic at all. I want it to be systematic. Yeah, so you say we have an edge 0, 3, right? In this case, we have edge 0, 3, and it's associated with this path. And it does not associate with any other path. So we can try to get this. I mean, if it's the only one, like I said, if it's the only one, then it works, right? But if it's not, because some edges might be part of one path, but that path can have other edges, and these other edges can be yeah, the other edges can be, I can see a test case that this will fail. Dude, how are we supposed to do this? Like, seriously, how are we supposed to do this? I have no clue. Literally have no clue. Especially the minimum, right? The minimum requirement. Okay, minimum requirement. And then to hit it. Minimum requirement. It made me think of Dijkstra, but Dijkstra requires that the weight to be none already. I mean, do you want to try on it? Don't do trial and error. I don't think trial and error is the way to go. Yeah, so you have the path. I mean, one way to trial and error is, let's say we have a path, right? And then I get this path. I make this path into the target, right? And then I have however many edges is inside. So we know the sum of these edges, okay? So that's what we know. Then we check all the others. Here, yeah, this might not be actually a bad idea, right? So again, we go from source to destination and we find all the paths, okay? And then it doesn't matter, we just pick one. We'll pick one path and say this is gonna be the shortest after we make the modifications. And we make this path the target, okay? So by doing that, whatever edges that's inside that path, we know the sum, right? We know the sum of them. So we're done. And then we check the other paths, right? We check the other paths. If the other path, as long as it contains one additional edge, right? That's not in the original one. It's contain one additional edge. And we can always set that additional edge value to God knows what. Doesn't really matter, right? Doesn't really matter. We can set to whatever it is, and then it will work. And in fact, we can actually try this to make sure this idea is correct by return this. But now this is like kind of the, I mean, this doesn't really mean anything, but we just want to see. What we can do is set 0 to 2, right? 0 to 2, we set this to however many, and then this one will still be right because this is not part of the path, right? It's not part of the path, so it still works. Because when it checks the answer, I'm pretty sure they just run a Dijkstra, right? When they check the answer, just run a Dijkstra to see if the distance is the target. So that's fine, right? So as long as we have an edge in a different path that's not included in the current one, then we're good, okay? So that's done. So the difficult part will be if another path contains exactly the same edges as the current one that we want to set to the target, right? Now, if they contain the same, well, if they contain the same, then what we can do, right? Hold on, we can probably sort the path. So the path shall be sorted by the sum of the edges, sum of the positive edges, right? So smaller the better, right? Smaller of that, and then sorted by the number of -1 edges. The shorter the better. So now we have a list of paths with smallest weight so far and the smallest number of -1 edges. Okay, so now we start from there, then we can try to work towards target. But hold a second. Again, after we prune, there's a lot of steps going on. So we get, okay, let me go back. I need to go back to the start. So here's the idea. So step number 1, we need to get all the paths, right? We get all the paths from source to destination, right? All the paths. I think this one DFS shall be able to do. I think DFS shall be able to do this. No repeating those. That's basically it. Second, if any of the path, right, contains only positive edges and the weight, the total weight of the path is smaller than target, then we return empty. Return this. That's an impossible case, which is exactly the same as this one, right? That's an impossible case. Step number 3, any path with all positive, right? Any path with all, no, actually not all. Any path's current weight. So any path with current weight of positive edges larger or equal to target, discard. We don't consider them because they're already larger or equal to hold on. There's another case. Sorry, any positive is smaller. Actually, we should like let's add another one. 3 is here, and then if an edge in a path, right, with all positive and weight equal to target, right, then we can fill the -1 edges with large values, and then we're done. Okay, so like we have a path already there and its weight is the target. So if that is the case, then, and that's like the smallest path, right? If that's the case, then we will what? Then we will get all the negative edges into positive, the largest positive, and then we return it. So we're already done. So now the number 4 case is we don't have number 3, right? So we say any path with the current weight of positive edges larger than the target, then we discard, right? Larger, don't equal to. No, we do equal to. If it's larger or equal to, it means we have the negative edge and we have positive edge, and the sum of the positive edge is larger or equal to the target. When that happens, those edges are done. They're not possible, right? So they will be discarded. So now number 5. So for all the remaining paths, right? When you say for all the remaining paths, these are possible, right? For all the remaining paths, then we'll sort, okay, based on what? I mean, we can base it on the current weight. And then we should sort based on current weight, right? Current weight from large to small. Yes. From large to small. Wait, hold on. Can we set it to 0? Positive. Assigning positive integers. We cannot assign to 0. Oh. We can do more pruning, right? Okay, because the minimum you can set is 1. So more pruning. So large or equal to target discard. And if the current weight, right, if the current weight plus the number of -1 edges larger than target, then we discard. These are discard. This means the current weight, even if all the -1 edges turn into 1, which is the minimum, we still larger, we still blow up. So then we don't consider them, so they can go. Then we have the remaining, right? Then we sort based on the current weight from large to small. And the number of -1 edges from small to large. So I want the top, right? The top of the array of paths. The top one should have the largest sum, right? And then if we have the sum is the same, then it should have the number of edges that's the minimum. Okay? So, all right. With that, now we will have, I'm going to try one by one. Okay? So for the top edge, so the first path, I'll have whatever the edges, right? We have the sum, we have the edges, the sum. We know that. Okay, that's what we know. Then we have to go through all the other paths to make sure that they can be created. So their weight can be created larger than the current one. Okay, so we go to all the other paths. And if the other path has an edge that does not exist in there, okay, that does not exist in there. Oh, edge that does not exist in there. Jeez. How are we going to try that? Sort? No, not sort. Does not exist in there. Set. Yeah, we okay, so it's going to be a set. So if the set, we say intersection, right? If the intersection, nah, not really intersection, shall be minus, right? Because I just want to know if there's anything that does not exist in the current one. So which means the new path, the edges minus the target edges, we have something left. That means that does not exist, and then it's good. We can always set it to, however we want. Okay, so that's good. Oh, we don't have to try them one by one. We just, we have the current target, right? We have the target path, whatever -1 edges, we set them. They're right there. And then all the other -1 edges, we just mark them to 10 to the 9th because that's the maximum we can get, right? The maximum we can get. We just set them to 2 times 10 to the 9th. That's fine. We just set them there, right? And then we check. Then this doesn't seem to be that bad. But hold on. You can set those. That's, I agree. But what if you have like overlap, right? Now the top, the current path, the target path you have whatever edges there. and then another path has part of that, right? Part of that. Then what? Have part of that, then what? Well, if it has part of that, then we need to make that part and those are smaller. Those are smaller. It made me wonder if I should sort them from large to small, sort them from small to large. Yeah, I think I probably should sort them from small to large instead of large to small. I think large to small doesn't really make sense. I'll sort them from small to large, right? We sort them from small to large. So now we get a first one, we have to fit a pretty big value, and all the other ones are bigger, right? Are bigger, so it's a higher chance that they will be bigger. Okay, so then what? Well, we can go through the whole thing, and then we'll identify, and all the ones that have extra edges are gone, right? Don't have to worry about that. They're gone. That's good, right? That's good. They're gone. So we'll have some the remaining paths will have the same -1 edges as the target one. Okay. Then we need to decide, right? Then we need to decide. Yeah, I mean it is. We need to find something that's not shared by everybody else. But you have to go through the sharing anyway. Yeah, so you have these, they're all shared. Okay, they share the same edges. And one of them is small and the other one is big. We can set one of them to the target. That's fine. And then for the others, huh? Maybe I should sort not based on the current weight, but sort based on the length. You know what? I changed my mind one more time. I think I shouldn't sort based on the current weight. I think I just sort based on the number. Yeah. I think I'll just sort based on the number of -1 edges from small to large. The first one we try will have the smallest number of -1 edges, right? Then all the other paths that have more edges, they are guaranteed to work. Yes, they are guaranteed to work, right? Because the target path has the smallest number of edges. And if a path has more edges, that means they at least contain one additional edge. And we can always set the additional edge to however we want. So now the only trouble is, oh my God, I think I might have solved this, right? And then the only trouble is the one that contains the same number of edges. No, not even just the same number of edges. It's exactly the same edges. These are the trouble, right? These are the trouble. And we just need to make sure among those, right? Among those, we'll pick the one with, I wanted to pick the one with the smallest value, right? With the smallest value. Because if you have smallest value, then this pair can be big. Okay, so now. We will sort based on, yes, we'll sort based on the number of -1 edges. And then we'll discard anything that have more edges. Okay, we discard them. Yep. Number of small to large. Discard all the paths that contain more edges than the one with min number of -1 edges. So this will leave us, right? So number 6, we say this leaves us with all the paths that have the same number of -1 edges, the same mean number of -1 edges, right? Well, then we can have different combinations. Then we just like pick. Then we sort. We sort these paths, right? We sort these paths based on current weight, right? Current weight from small to large, right? Then we sort these based on the current weight from small to large. Then we pick the smallest weight, right? We pick the smallest weight, which means those edges have to be very big. And then because they're big, yes, I think that's it. I think this is it. This is it. Well, I think implementation will take a while. I'll give it a shot, but I only have like 9 minutes left. Let's see, you think you can implement this in 9 minutes? I'm not sure. But I have a plan. I have a plan. Okay, hold on. Let's try this. All right. So first things first, I need to find damn it, I need graph. Default dict. So I need graph for sure. So I say graph equals what? Equals default dict list, and then for a, b, and value, I'll say w in edges. Graph a dot append b w, graph b dot append a w. Okay, so def dfs, what do we want? We want to find the path, right? We want to find the path. So we have the current node, and we need a path. That would be a list of list int, right? Because the path, and not really the path, right? It's going to be the edges. Yeah, that's just kind of so paths. What do you do? Edge groups, edges, group of edge, group edges. Okay, so the group edges is in the path. Okay, visited. Need a set. What else? Set. Don't return anything. So all I want is to find the group edges. So then we can say all paths. Okay. So we just go through. Let's make the DFS very simple. Okay, we'll make it very simple. If node is invisited, just return. Okay, otherwise visit add node, and then for child weight in graph node. Okay, in graph node, we can say group edges dot. We can do append because I don't think we'll have a duplicate. So we can append what? The current path. let's make sure that we can just do min, max, and a weight. Okay, node child, right? So we'll add this, and then we will say DFS child group edges visited, right? And then we'll backtrack. Once we're done here, we will do group edges dot, we'll pop it. So of course, we also need to say if node visited, we'll return, all right? And we'll say if node visited, we'll add it. Oh, we'll add it. Group edges need to do this, and the visited need to pop as well, right? At the end, visited dot remove. We had to remove node as well, right? Because we DFS, right? We go. Once we're done, we backtrack, right? We backtrack, and then we visit something else. That might probably go there as well, right? And then we backtrack, backtrack. I think this should be good, right? We're trying to find all the paths leading from this to the node. It kind of made me feel BFS might be a better way to do this. Yeah, if I do BFS, what's gonna happen if you do BFS? Is it DFS? I'm not sure. DFS. Yeah, I think it should be fine. All right, we add this. We probably don't. Now let's just say if node is equal to destination, okay, then all paths dot append. Dear me, I need to put group edges into it. But no, we can do the pre-processing here. So we don't put group edges in it. We'll go through them, calculate the current, we'll follow our steps. Okay, we follow our steps here. So we do this kind of pruning here already. Okay, so node is equal to, and then we'll return. Now we don't have to add node to it. So node is equal to, we already add the path, right? We add the path to node and we come here, and then we say node is equal to, that's fine. Then we need to go through the group edges, right? So we can say the current weight, okay, so current weight equal to 0. And we need the edges as well. So we say for AB, W in group edges, if W is, so group current weight and negative edges is equal to this, right? If this is larger than 0, it can never be 0, right? It can never be 0 because the edges is -1. Yeah, it can never be 0. So if it's larger than 0, then current weight will be plus equal to W. Else, we can say negative edges dot append AB, or append AB. Okay, append AB. Yeah, so we have this edge, this AB edge. And you know what? We might need to, let's just do tuple, just in case. So we'll append this, right? We'll append this, and then what? Then blah, blah, blah. We go through all things, and then we say if, okay? So now we can go back to here. I think it's, well, getting this, if any of the pack contains only positive edges and the total weight. Ooh. Ooh. Oh. What do you think? Okay, let's just clear out anything that's larger than target. Okay, if it's already larger than target, then we don't consider it. If it's smaller or equal to target, then we consider it. We say all paths dot append. We're gonna do, the first is gonna be current weight. Second is gonna be negative edges. So we do that, right? If this is smaller than target, we do that. And then we return, and then we keep doing this, okay? So I think that shall be good enough. So we can do DFS. Node is gonna be the source, right? Source, group edges, we don't have anything, visited as a set. So we do this, then we'll get all paths. Okay, we'll get all paths. Let's give this a shot. Give this a shot. I need to make sure that we are correct at every single way. The edge, not edge case, the I can write the test, but that requires me to go through a Dijkstra. I'm not sure if I'm in the mood, at least not right now. So I'm not gonna do it right now. So I'm gonna try is just to make sure that the logic is correct, and that should be good. Oh my goodness, I have n edges, source, destination, target. Modified. All right, let's just do this. All I want to know is, let's just print all paths. Okay, so this is the path, right? So we have 0 to 3, 3 to 4, 4 to 1. Looks good. You know what, I mean, with this we can do all of them. The second one is empty. The third one we have an empty. Yes, and we have 5 and a 0, 3. So far so good, okay? So far so good. So now we're gonna go through all paths, right? Go through all paths. We say for current weight and neg edges in all paths. If, so this is first done, right? And then we're gonna filter all paths. We call it filtered paths, okay? If current W is larger, is larger than target, or current is equal to target, or this is equal to target and len negative edges is larger than 0, right? In these two cases, continue. So these are, don't consider them, right? And then we say if current is equal to target and not negative edges. So this, right? This we shall set everybody to, well, we can break. We'll break. instead of break, can we just fill? Yeah, we can. We'll just change the edges, so we can turn, right? We can turn any -1 edges. We can turn all the -1 edges into whatever large value. Then we can say return for A, B, W in edges. Okay. And then this will be A, B, W if W is larger than 0. Else 10 to the 7th. 2 times 10 to the 7th. 2 times 10 to the 9th. Max value. 2 times 10 to the 9th. So we just set it to max value. Okay, so now it's gonna be current weight is smaller than target, right? It's smaller than target. And if we don't have edges, if current is equal to target, actually more, all current weight is smaller than target and not negative edges, these all not gonna, we cannot do. So now these are current. Now we have current weight is smaller than target, and there are negative edges. So these are the things we can play with, right? These are the things we can play with. Filtered path dot append current weight, current weight and negative edges. Okay, then we say if not filtered path, there's nothing, we have nothing, then we'll return this. If we have something, then we're gonna sort. That sort key equals lambda. We will have key equal lambda tuple. We'll have len tuple 1. Okay, and so small that, and then tuple 0. Okay, so yeah, we basically just pick this, pick the first one, right? We just pick the first one. So we pick the first one, and then we say that is going to be what we need. Right. Okay, so the first one. Then we say required sum is equal to target minus filter path 0. Okay, we require sum, and then we need to just fill everybody's 1, and the last one just fill. Then we need to go through, and we have an easier way to find what their values are. Graph neg edges dict dictionary. Okay, if W is smaller than 0, negative edges dictionary of this min max. Okay, min max equal to W. Nah, because I have to return all the edges, right? I have to return all the edges. Now we can just say edges dict. Edges dict doesn't really matter. I just need edges dict. So edges dict equals this. Okay. Then we can say for AB in filter path 1. Okay. Filter path 1 all the way, but excluding the last one. Okay, excluding the last one. Then we say edges dict AB. Oh, we can say for edge. Okay. And this can just be edge or equal to 1. And then edges dict filter path the last one shall equal to target minus len filter path, because everybody all 1, so minus 1, right? And then for all the other, we'll just set them to, okay. Then we'll return for B, W in edges dict dot items, okay, dot items. Then we're gonna do A, B, W if W is larger than 0, else max file. Oof. Alright, we'll just give this some shots. If these are not correct, then we will call it for today. Does it work for this? Node, what? Oh, there ain't no node. Dude, there's A and B. A, B. A, B. List out of range. Oh yeah. Filter path is no 1. What are you doing? Filtered paths is just filtered paths dot append current weight and this. So we sort it and then we go through this. We have this we don't need. Then we just need the edge. Right? Filtered path. No. Filtered path 0. Oh my god. 0, 0, 0. I want the top one and then 1. Yeah, this is not right. This is gonna be edges dict filtered paths 0, 1. Right, these are the edges. This is the last edge equals this. Okay, try it again. Yeah, filter paths 0, 0. Minus 0, 1. Lots of error. Lots of error. You know what? Filtered paths dot sort. we should say target path shall equal to filter the path 0. Then all of this can become target path. Right? Target path I have current, that would be much easier to reason with. So target path, this is good, and this is not going to be this. This will be target path 1 minus target path 0, that's the value, and then this is going to be target path 1, and then I'll return this. All right, let's try this. All right, you want to try? Yes, go for it. Who knows? All right, who knows? Go for it. Oh, maybe it's a DFS. Yeah, maybe it is DFS, I think. Nope, it's not DFS. It's wrong. How many did we pass? Oh yeah, we passed a few. We passed a few, but it's not enough. Alrighty. Expected. Oh, I think we didn't consider everything. Shoot. All right. Hey, we save this for tomorrow. Man, I have high hope. Okay, high hope for this method. I think it will work. I just need to work a little bit more on this. Basically, that's what it is. All right, I'll see you guys tomorrow. Adios.